Hi, this is the fourth part in a 5-part masterclass on time series in Stata. Today, I'm going to show you the most powerful tool at your disposal. A good scientist questions and verifies everything. I'm going to show you how to prove to yourself if the statistics work using the power of Monte Carlo simulations. I'm going to show you how to generate artificial data and to extract hidden p-values and key results. And then in our example, we'll look at why, if you're not careful, you can get spurious regressions 80% of the time. All right, let's go. You can find this program file using the link down below in the description. Today, we're going to be simulating our own data. In fact, we're going to start with 100 observations and just generate our own time series, which are very easy to do in Stata. We're going to generate a time variable that's just equal to the row number and tell Stata we're working with time series data. We can always verify to see that this ran correctly, and we can see that we have our time variable with 100 observations. We're going to set our seed just so we can get the same result every time and have our results to be reproducible. We're going to generate 2 random draws from a standard normal, calling it E1 and E2. These are just random draws and are completely unrelated. Then we're going to construct the random walk by taking the sum of those random draws. Stata always starts at the beginning of each time series, so we're going to get a cumulative sum of the random draws, which you can verify here yourself. The next thing we're going to want to do is look at these completely unrelated time series and see how they are correlated. And in fact, in this plot, it actually seems like, despite being completely independent from each other, there is a significant correlation between these 2 time series variables. And this is surprising because both of these are random draws and are completely independent. And we can verify this by just simply running the regression. And our regression shows that with 100 observations, we have a significant correlation between our 2 variables that is highly significant. So what we need to know, is this just luck of the draw, or is this a systemic problem? That's why we're going to simulate this thousands of times to find out. Because we're going to be running thousands of simulations, we need to know how to extract the results from each simulation. Because this differs by command, the best thing to do is just carefully read the help files, because at the bottom, you will get a list of everything that's saved, both scalars and matrices, from every estimate. We can actually see this in more detail for the specific estimate by typing eReturnList. This tells us the exact scalars that we can recover just by calling these names, as well as the exact matrices. For example, we can see that our adjusted R-squared value, 0.26, can be recovered just by creating a scalar equal to that value. And here we can verify that by displaying it. We can also print the coefficient matrices and the covariance matrix. However, the p-values are not recoverable. So there's 2 options to recover your p-values. The first is to extract the coefficients and their standard errors from those matrices and calculate the t-statistic yourself. This is totally doable, but may be prone to errors. The second thing is to steal from the hidden matrix. What's the hidden matrix? Well, in our regression output, we have the estimates and a number of calculations that are using those coefficients and the covariance matrix. And we can actually recover that precisely by using this rtable command. And when we print that, we can see that we've got all the estimates. In fact, the 4th row of the first column is just the p-value from the regression. So we can save the t-statistic and the p-value just by extracting that cell from the matrix. It's that easy. Now for our simulations. At the very beginning of our simulation section, we are going to set the parameters which are going to govern the features of our simulation. In particular, the variance from the random draws, how many simulations we want to take, the number of periods in our sample, and any burns that we want to do at the beginning to make sure there's no starting point effects. These are going to be saved as local commands, which means we need to run all the section at once, because these are just going to be temporarily saved as text to feed into the simulation program at the bottom. So let's look at the program we're going to create. The very first thing that we're going to do is make sure that if the program, my sims program, which is just my name for the simulation, exists, make sure to drop it. The capture is a way to tell Stata to run a command, and if it fails, don't worry, keep running. So my program might not exist, in which case it says, I can't drop the program and keeps going, or it exists and it just drops it. Now we're going to specify our program. The program is our class. Basically what this means is that it's going to return whatever we tell it to. So we specify the program, we give it a whole bunch of commands, and within the program, we tell it to return our scalar. So here we have our regression, and we're saving the t-statistic and the rejection rates from the regression. And we are returning it as a scalar and saving this value. And so that when we simulate will be able to see whatever we want to return. So here we're using the R as the t-statistic to return. So we type the command simulate plus any variable that we have set to return within the program. Then we set any options, including the number of simulations, which is passed down from above, as well as any seed that we want to use inside the program, again, to ensure reproducibility. Then we specify that we want to run our program. We then have the option to pass in any information into the program, and we do this using arguments. Here we have a list, the variance, the number of periods, and the observations to burn at the beginning. We specify these at the beginning in our local commands, so they're just going to be typed in here automatically for us. These arguments are passed into the program using this args at the very beginning, which will take in the first variable from that list and call it VV, which we know is our variance, then our sample, then the number to burn. You can see here that we set the number of observations equal to the desired sample plus the number to burn. We set this as equal to our observations. Then we generate our time variable like before and simulate our data. So now we have both of our random walks. Then we drop any observation that's before the number of observations we desired to burn. This will give us our final sample. Now, one thing is that we cannot run section by section within a program. However, what we can do is run the program and intentionally get it to crash. Let me show you an example of this. So if we run this whole section and get it to crash right after it creates the data, it says, hey, I don't know what crash means. Well, that's intentional. We wanted it to crash. And so what we can do, a great way to check to see if your simulation is working, is actually, once you've created the data, go make it intentionally crash. And here we can see that we have 100 observations from 500 to 600, and we have two series that very much look like a random walk. So we can remove our crash command, and let's take a look at what we're doing. We have our regressions where we're saving the t-statistic and the rejection rate, and we have a nice little command here that embeds an if statement. So if the p-value is less than 0.05, then create a 1 if it's significant or 0 if not. So we should be able to return a series of 1s and 0s that will be able to tell us whether or not that pass of the simulation was significant. The other thing we're going to do is actually estimate the regression correctly by estimating the data in differences. Because the original series are non-stationary, by taking differences, we are ensuring that the data becomes weakly stationary so that it'll have a constant mean and variance. And similarly, once we run this regression, we can save the t-statistic and the rejection rate. Here, the variable that I'm returning is the t-statistic from the regression in levels. Here I'm returning the t-statistic for the regression in differences. So now we can run this entire section. Recall we have to do that because we are using these local commands. And Stata is now going to do our 500 simulations as requested. Once we've completed the number of simulations, we can look at the data and see the return variables. Here, we should have 500 return variables showing us our t-statistics for the regression in levels, as well as whether or not that regression was significant at the 5% level, as well as our t-statistics and a rejection rate for the regression and differences. Our simulations are complete, so let's see how much of a problem spurious regressions can be. We're going to summarize the rejection rates from both the model and level and differences, and we're going to save that average as a local command. What's nice about the local is because it's being treated as text, is we can use it later in our subtitle, which will make for nice graphs. When we summarize the two rejection rates, the first thing we can see is that 80% of the time, the regression in levels is showing significance. This is spurious regressions. We know that these two variables are independent, yet 80% of the time you would find significant correlation. When we estimate their model in differences, however, we see that the rejection rate is very close to the level of significance. This is much more sensible and shows us why we need to be very careful to make our data stationary before modeling it. Then we can graph the t-statistics for both the model in level and differences and combine them in a graph combine program so we can see them all together. Recall that we're going to run this whole section at once because of the use of locals. The histograms of the t-statistics reconfirm the results. 80% of the t-statistics are outside of the critical values when we estimated the model in levels, just showing us how severe spurious regressions can be. I'm calling them spurious because it's an artifact of our assumptions when we constructed our tests and models and not a true feature of our data. We know that the random walks are independent. In contrast, we can see the t-statistics for our model estimated in differences are giving us a rejection rate very close to the level of significance of 5%. Our rejection rate is only 4% because we had a pretty small sample and a pretty small number of observations. You can play with it yourself to see the appropriate number of observations and increase the simulations to 5 or 10,000 because asymptotically, that is, the more simulations that we run, this should approach the 5% level. You now have the power to simulate to verify any method and how well it works. In the next video, I'm going to save you hours by making sure you never copy and paste and to automate all your output in seconds. Make sure to like and subscribe.